right. Thanks for the introduction. So, yeah, today I'm going to talk about, the status of hybrid I/O. The last talk here was like 2 years ago. That was made by Patrick, and I want to give an update on, what's going on there. So, there we go. So, first of all, let's give you a little bit of an abstract and maybe jog your memory on hybrid I/O. We already heard it before today. But basically, hybrid I/O is a new data path in the Lustre client, and it combines buffered and direct I/O, particularly the benefits here. And it relies, so the main trick behind this is that relies on unaligned direct I/O support and removes memory alignment requirements that you would otherwise have. And the whole thing is completely transparent to the application, so that means that the application doesn't know that hybrid I/O is in use, it just gets better performance, and it has no impact on any strong consistency guarantees here. So, and today we'll talk about, exactly that. What is hybrid I/O v1, or what we consider v1, and what made it into Lustre 2.17. The last time we were before pretty much 2.16 when we had the talk, and then some research that kind of happened at the same time while hybrid I/O was developed, that looked into additional features that could be used in the future. And then for hybrid I/O version 2, this is exactly what, which one of these we could consider there. And just already some notes on the numbers that I'm going to have here. So they should be understood as general guidance, right? It looks specifically on the, the trends and the relative numbers. The differences are pretty big, but not on the specific numbers, right? But I give the experimental setup later anyway. So. Right, so let's talk about, the Linux default mode. This is where everyone is familiar with, right? If you're using your write, it's using buffered I/O, it uses the page cache. But there's also this alternative direct I/O, which bypasses the page cache, right? And it can be more beneficial in certain situations. So let's look at some performance here. So what we have here is a local LDISC FS benchmark, and this kind of setup that you see here in the figure will happen all the way through in this talk. So you have on the y-axis the throughput, and on the x-axis you have the I/O request size for every write, right? And so we compare here buffered I/O and direct I/O for reads and writes, and the horizontal line here, you see the most, nice. So the horizontal lines here, this is buffered I/O, and you see that basically the performance stays kind of the same, but for direct I/O this is different, right? For direct I/O it's pretty terrible at 4K. But then eventually there's kind of a break-even point where it's much better than buffered I/O. So they don't compete really for the same workload, but there are specific places here in terms of I/O sizes where one is better than the other, right? So why isn't direct I/O more used, right? So generally users tend to use the more familiar I/O mode, right? Because direct I/O also has some alignment constraints. Specifically, it has to be multiple of page size and aligned to the page offset, and it's often unclear which I/O mode performs better. And the idea of hybrid I/O is basically to change that transparency so that users don't have to deal with it. So let's look at the specific pros and cons very briefly for each of these, for each of these modes. So for buffered I/O, again, this basically just means uses the page cache. And so it's flexible in the sense that there are no alignment requirements because writing to the page cache gives you that alignment. And it also allows read ahead and write aggregation, which is really important for these small I/O requests, right, to get good performance. This is why a couple of slides ago, right, you saw for 4K, you had, a decent performance there. The problem is the page cache is, shared by all the other processes, right? And so you need to lock them. And that really hinders the scalability here. So there's a significant overhead overhaul for cache management there. For direct I/O, this means direct from user memory, and it bypasses the page cache. So because it bypasses the page cache, there's no locking included here, and it scales quite well for large I/O sizes, right? But at the same time, especially for small I/O sizes, you really expose the latency of the disk, right? This is why it's so slow. It requires memory alignment that users need to take care of. And so, it's not as flexible here. And so hybrid I/O, tries to do the best of both worlds here. So V1 was exactly that. And this was released with Lustre 2.16. And it automatically, so there was a specific threshold there, and it automatically switched between buffered and direct I/O within the file system without the user knowing, fully transparent between both of those modes. There are different read and write thresholds. For reads, we take a little, you can use bigger I/O sizes to switch to direct I/O because read ahead makes buffered I/O more competitive longer. But in any case, these thresholds are customizable. And since Lustre 2.17, then hybrid I/O is enabled by default. I want to mention here that there were some alignment issues found in 2.16, so we don't recommend using hybrid I/O in 2.16 and opt in here, but these were resolved for 2.17. So let's look at some performance numbers. So this one seems familiar. We saw this maybe an hour ago in Sebastian's talk, and also 2 years ago in Patrick's talks. And you see here you have buffered, which is the black line, and you have direct I/O, which is the teal one, and we have hybrid. And so what we have when we enable hybrid I/O is that it basically follows the best of both worlds, right? We start with buffered I/O, right? We go up here, and then later we follow the direct I/O line. Of course, because we have to align that buffer, so that means we have in the file system we have a bounce buffer basically where we have to mem copy the user buffer into. This costs some amount of performance, right? So this is why we don't exactly reach direct I/O performance, but it's still 16 times faster than buffered I/O, right? And this is just a single process writing to a file. So for shared files, we still only are at a single client, but here we're now scaling the processes, right? So we're fixing 4 megabyte writes, and that means for hybrid I/O, we always use direct I/O because it's above that specific threshold of 2 megabyte. And in that sense, what you see is, well, buffered I/O doesn't scale at all, right? You end up at 128 processes with less performance that you had with one, right? And if you use hybrid, well, it's 52 times faster, right? So this is really exciting here. And we see later how that actually looks like if you have that from multiple nodes in an IOR hard an IOR hard workload, for example. So that is what you have in 2.16, right, and 2.17 by and large. And so at the same time, while 2.16 was wrapping up, there was some research happening, right? And this is what we called auto I/O. And I specifically have another name here so you don't get confused. So auto I/O is basically this proof of concept research prototype that we had. And that was published at the FAST conference 24. This specific paper has a lot more details into that and more extension than what I will go through here. But it's open access, so you can read it anytime, right? There's nothing to pay here if you're interested. So auto I/O was based on, as I said, 2.15.58. And we wanted to see basically what kind of additional things we could do based on hybrid I/O to make this even better. And one of those was a decision window, right? Where we said, okay, well, maybe we don't only have one threshold, we have two, more on that later. But in this case, like, the file system state can be taken into account, right? Where we could maybe use direct I/O for smaller I/O sizes already. Then we have another optimization, which is server-side write-back and delayed block allocation. We've also heard that before today. More on that later. And also cross-file batching for buffered writes. That is an optimization, if you have a bunch of small writes, you can also batch those together and write them all at the same time. But I won't go into that today and only go into, the first two. So this specific paper here, just to wrap this up, was a collaboration between DDN at the university where I was working before. And yeah, again, there's a lot more experiments there, so feel free to check that out. I will only look at two of specific experiments and highlight those here. So, but first about the decision window that I was talking about. So this specific blue line that you have here, this is kind of the threshold that we have in hybrid I/O, right? Everything which is on the right of that is direct I/O, and everything on the left of that in hybrid is buffered I/O. And what we did with auto I/O is basically where we said, well, if we look at the state of the file system, like if we have a lot of log contention on that file, there could be kind of a window where direct I/O could be more competitive, right, than buffered I/O even earlier. So we have like two thresholds. We have one here between 16 and 64K, where we say, well, in any case, whatever is happening, buffered I/O is always faster. And then in between, we have this decision window. And then basically the direct I/O threshold just moves to the left. But of course, what does that mean? What does log contention actually, result, or what effect does it have on performance? So in the next slide, I have a, straighted I/O over 10 nodes, which is kind of an IOR hard workload, right? So a lot of nodes writing at the same time to a single file, and there you have log contention, right? And what you see here, so this is basically just an experiment where we played around with the I/O threshold, but basically what that means here is that if I go back for a second, where we had a 2 megabyte kind of a toss-up between direct I/O and buffered I/O, now it's like at 256, right? And at that point also the experiments become a little bit unstable in terms of performance. It changes a lot, but in general, direct I/O becomes beneficial much earlier. The same we have for, under memory restrictions, right? If you only have a little bit of memory available and you just stream it to a file but never read it, well then everything that you write to the page cache is basically overhead that you don't need. And in that instance, you can also, start direct I/O earlier. So again, you see here that the direct I/O, which is the blue bars, get, at 256, you already have that toss-up, where previously without that, you would have it at 2 megabytes. And so this is the idea of auto I/O, that at that point you can use direct I/O and be beneficial for performance. So other optimizations here is the server-side write-back. So when we have non-rotational disks on the OSTs, basically what Lustre does is direct I/O on the server side, right? And that also means that for small I/O operations, we against the latency, we expose the latency of the disk, and basically the writes are synchronous. And the idea is similar to what we have on the client side with hybrid I/O. We could have something similar on the server side, in which we say, well, if we have everything under 64 kilobyte in a write request, this just goes to the page cache, right? And then we immediately go back to the client, and then this works similarly as buffered I/O on the client, right? You would flush that after a couple of seconds. But you can also have write aggregation and write a full stripe basically to the server, or you call fsync, right? This is what you can also do. Very similar to buffered I/O in that sense. On top of that, you could do delayed allocation, in which you defer the block allocation until you actually flush, right? And this then again also helps performance. So less file fragmentation and fewer extents on the disk. And we see this in experiments later. All right, regarding the experiments. So the servers here we're using in the next experiments DDN appliances with an NVMe backend and 32 client nodes. But we also compared against other file systems. And why specifically these two file systems? Well, BGFS, which is a parallel file system that is built in Germany, has a similar mode where it can switch to direct I/O. This is this native mode, right? And this is very interesting to compare to it. And then for OrangeFS, there's on the server side two I/O modes, at least for that specific version. This has changed since then. But here direct I/O is this direct I/O mode that we have on Lustre, like similarly. But we also have this alt I/O mode, which uses buffered asynchronous I/O. So similar to the server-side write-back here. I don't want to really go into detail in the experiments with comparing against these two file systems and focus on Lustre. But in the paper, we're going very deep into the differences here. And I want to say that every experiment and the setup that we have in the paper, that is all available as artifacts, right? So you could set up these file systems and Lustre with a specific patch, all in the same way, and you can basically, reproduce these experiments, right? And this is all available here on the Zenodo archive. Right, so the first experiment that I wanted to highlight is IOR hard, right? So IOR hard is, once again, a strided I/O workload, as I shown before, writing to a single shared file, and part of the IO500 challenge. So the workload here was we're using 10 clients with 16 processes each, so 160 overall. And I want you to focus here on the blue bars, right? This is because this is all Lustre, or the leftmost 5. And we first start on the right side of the house here. So we have the Lustre buffered I/O, which is this one here, right? Then we have the Lustre direct I/O in the vanilla versions without hybrid I/O or server-side write-back. Then these two add server-side write-back, and the last one also adds auto I/O, server-side write-back and delayed allocation. And so you can already see that server-side write-back alone has some improvements here for this small strided I/O, right? But for auto I/O and delayed allocation is even bigger. So first of all, auto I/O is run. So for IO500, you can say, do I want to run this benchmarks with direct I/O or not, right? By default, we run it with buffered I/O, but because of auto I/O, and because it detects a lot of log conflict, it switches to direct I/O, right? And if you couple this with delayed allocation, all that, you get quite a good speed up here. So overall, compared to buffered vanilla, this is 4.4 times the performance that we had. So for the read part of it, there is no lock contention, and so auto I/O stays in buffered I/O and does not switch to direct I/O. And because of that, basically, the buffered I/O cases that we have here, they kind of stay the same, right? There's not really an impact here. So this is very, very nice results. So you get, very easily 4 times the performance just for this very hard workload alone. But okay, this is a benchmark, right? And we can't only have micro benchmarks, so let's also look at a real application. So, and the one I want to highlight here is NEC 5000. This is a computational fluid dynamics application. This is a very typical bulk synchronous application that you see in HPC. And what it actually does here is we have 512 processes over 32 nodes, and they collectively write at every step boundary to a single file, right? And this is 600 megabyte big. So the idea is here generally that, the more often you write, the higher resolution you have for your simulation, right? Typically, based on my experience, people don't do this because the parallel file system cannot keep up, right? And so you do it, I don't know, every 5 or every 10 steps, something like this. But yeah, in this case, for this 10-minute workload that we had for this turbulent flow, we generated around 600 gigabytes of data, right? And the interesting part of it is, compared to micro benchmark, where you have a set I/O size, here you have a nice I/O size distribution, right? So you have very small I/O that, if you have hybrid I/O, would always stay in buffered, but you also have a very large one where it would stay in direct I/O. But here in the middle, these ones again could be direct I/O or could be buffered I/O, depending on the state of the files. Right. So if we look at the results here, again, the blue ones are Lustre here. We see also the speed up once again. So we have Lustre in the vanilla mode, so buffered I/O. Then if we have auto I/O, we already get an improvement. And then server-side write-back gives another improvement, I think around 10% here. But overall, it's like a 1.4 improvement. And what is very nice about auto I/O is that you can also look at the I/O statistics, right? So that means you can look what type of I/O was switched to what mode and because and for what reason, right? So again, there were like very small I/O operations in there. So a lot of those were staying in buffered I/O because of that. We had very large I/O requests that stayed in direct I/O because of that, right? This is this part. But these ones here, these were all switched to direct I/O because of lock contention on the file, right? And so only 65 of those actually stayed in buffered I/O, right? Which is the default case for this decision window. So yeah, very nice even for real application. We have more in the paper, like VPIC, for instance. So this gives us kind of the segue to hybrid I/O v2, right? And for hybrid I/O v2, there was always this idea that we want to switch to direct I/O under more conditions, where we know that it improves performance. And this was specifically kind of the case that we've just seen, right? We can include lock contention or memory pressure and all that. And all of these parts that I will list here can be considered for version 2. So the first one is lock contention detection. I have here the ticket number and the patch, if anyone wants to take a look. These are kind of active. And basically this works that the server counts the conflicting locks over a sliding window, and then on the client there's a specific flag that is set. In the paper this was around, when we detected that the file is contended, then it stayed that way for 30 seconds. And nowadays it's a little bit less. I think it's like 4 or 5, something like that. And then the second patch here is then introducing the decision window. There's more stuff to do here, but the lock contention patch is very active here. Then the next part is hard drive aware thresholds. And the idea is basically that if we have a hard drive, then read ahead also makes it that buffered I/O is competitive longer, so with higher I/O sizes, and so we would switch to direct I/O later, right? This is not a big change, but an impactful one, right? Then another one is the server-side write-back, what we just talked about. Not specifically delayed allocation. This is a separate patch, and there also seems to be more work that needs to be done there. Server-side write-back. Again, small writes hit the server page cache, and so something for hybrid I/O that we have on the client, similarly on the server side, beneficial for these kind of IOR type workloads. And so if you remember, 2 years ago there was, Patrick talked about the direct I/O path rewrite, and parts of that has happened in the past year. And basically this converts the CL page state machines to simple page arrays. And some early experiments showed that direct I/O there increased to about 100 gigabytes per second per thread, right? Which is pretty high. And so for hybrid I/O, that means that that the 20 gigabytes that we see back then would just go up a bunch, right, to 45 gigabytes a second. So however, this seems to be superseded by large folios, and large folios, of course, we just heard. And it's currently not clear if that will be continued or not. It seems not, but we'll see. And then again, also for large folios, we need to see the performance there and if there's still something up for the table. But in general, what large folios gives us is just a lot less bookkeeping overhead. And so again, this narrows the gap between pure direct I/O and hybrid I/O, where then the bounce buffer that we have in the client kernel is the remaining ceiling. All right, to recap and close up. So again, hybrid I/O combines the benefits of both buffered I/O and direct I/O. It's completely transparent to the application, doesn't change the typical strong consistency semantics that we have at all. For buffer performance, you get buffer performance for small I/O, you get direct I/O like scaling and performance for large I/O. And if you still want to use AutoDirect and force direct I/O, you can still do that, and hybrid I/O doesn't affect that at all. And hybrid I/O is enabled by default since Lustre 2.17. We talked about Auto I/O with this research that happened a couple years ago that explored some extensions. And for hybrid I/O v2, we want to include some of those findings in there and make that ready to be landed. And that includes lock contention detection, that decision window that I talked about that made Auto I/O, server-side write-back to improve small I/O on the OSTs, and the HD-aware threshold. And yeah, that's it from my side. Thank you very much.
Any questions for the speaker?
Thank you. I browsed the paper a little bit as you were speaking, and I was curious, did you do any thinking about the, like considering hardware signals in terms of how you kind of follow that decision window? Or
Oh,
are
no,
you-
no, then, no, not that I know of, no.
Okay, a little like the back
Oh,
in the
that wasn't
storage
in the
type.
paper, no.
Okay,
Yeah. Mhm.
gotcha.
But yeah, interesting idea, yeah. Thank you.
So when you open a file ODirect or OSync, it passes a flag to the server during the I/O saying that it should also sync the I/O to disk before returning a result to the client. When you're doing a hybrid I/O and it chooses to do ODirect, is it also directing the server to do a sync?
Well, yes, it is. It's completely synchronous on the server side without the write-back cache, yes. Good question about the OSync, if it's the write-back cache, the server-side write-back. I'm not sure, I suppose, yes. That we would need to force a sync then, yeah.
That makes sense.
Yep.
Any other questions for our speaker?
Sorry, just to kind of back up what Timothy was asking. So a user can basically, if they send an ODirect or OSync, they can basically render the hybrid I/O. Basically, they can supersede or bypass that, correct?
Yes, if you're using ODirect and force direct I/O for a file, yes, then hybrid I/O is not, well, used basically.
Not in play.
It's bypassed.
Okay.
Yeah.
Are there any metrics associated with that so that you can tell which strategy was chosen?
Sorry, can you say again, please?
Yeah, are there any metrics that are associated or available that allow you to see how it's performing? To see which strategy was chosen, for example?
For hybrid I/O, I don't think so, but I'm not sure. For auto I/O, yes.
Okay.
Yeah. I guess that would be something that we can include, right? Because we already have it in this sense, but I'm not sure if it's there for hybrid I/O. Yep. Okay. Okay, thanks.
If there are no more questions, please give our speaker another round of applause.
Thank you.